Long before mechanical clocks ticked across centuries and before telescopes revealed the hidden reaches of the heavens, there existed a device of extraordinary subtlety and intellect, one that carried the motions of the cosmos into a tangible form. Found in the remains of a Roman cargo ship off the Greek island of Antikythera, this device, now known as the Antikythera mechanism, was a collection of interlocking bronze gears and engraved plates arranged with astonishing precision, designed to track celestial cycles, lunar phases, and even the schedule of the ancient Olympic Games. Imagine the gentle currents of the Mediterranean brushing against the corroded bronze, as if the sea itself were whispering secrets of human ingenuity long forgotten. Its discovery in 1901 by sponge divers was the beginning of a journey into an ancient mind capable of compressing the universe into a small handheld instrument. The origins of the mechanism are traced to the Hellenistic period, approximately the 2nd century BCE, though its precise inventor remains unknown. Scholars suggest it may have been created on Rhodes, where astronomy, mathematics, and philosophy flourished. The device itself is roughly the size of a shoebox, yet inside lies a miniature cosmos with dozens of gears, some intricately cut to allow differential motion, a principle modern engineers would only rediscover much later. Each gear reflects cycles of the sun and moon, and some reconstructions indicate it may have also accounted for the positions of the 5 planets visible to the naked eye. The sophistication of this construction is staggering, implying that its creator had not only mechanical skill, but also an intimate understanding of astronomy and mathematics far beyond what most civilizations would achieve for centuries. Functionally, the Antikythera mechanism allowed its user to predict solar and lunar eclipses, a tool for both scientific observation and ceremonial planning. The front face contained dials for the calendar, showing the months, days, and perhaps zodiacal positions, while the back plates revealed the Saros cycle, a period of approximately 18 years over which eclipses repeat. These calculations were not mere curiosities, they were essential for scheduling religious festivals, agricultural planning, and even advising political leaders. The mechanism may have also marked the cycles of athletic games, integrating human societal rhythms with the vast movements of the heavens. Its purpose was at once practical and philosophical. It allowed humans to impose order on the apparent chaos of the cosmos, to feel a sense of mastery over the relentless progression of time. The gears themselves are remarkable in their design. Some are compound gears, with smaller teeth interacting with larger ones, allowing the device to model irregular lunar motion. Others are simple but precise, forming a chain of rotation that could translate a single crank motion into multiple synchronous outputs. The inscriptions on the device, written in Greek, describe celestial phenomena, possibly giving instructions for interpreting the dials. Its construction demonstrates a level of miniaturization and mechanical understanding unmatched in the ancient world, a fusion of engineering and astronomical observation. The Antikythera mechanism embodies the idea that knowledge and craft can merge to create objects that both measure and teach, and in its gears, one sees the faint echo of a human mind reaching toward the infinite. Its use would have required patience and knowledge. The mechanism may have been in the hands of astronomers, philosophers, or scholars, perhaps in the observatories of Rhodes or Alexandria, guiding them in the study of celestial mechanics. Turning the small hand crank, an observer could watch the movement of the sun and moon, anticipate eclipses, and align civic or religious activities accordingly. This tactile interaction with time and space, centuries before the invention of mechanical clocks, reflects a different understanding of the cosmos, one in which observation, calculation, and physical manipulation were inseparable. It is easy to imagine a quiet scholar in a stone room, turning the bronze gears under the soft light of a lamp, tracing the motions of the heavens with fingers that could feel their rhythm and precision. Despite its brilliance, the Antikythera mechanism was lost to time. Its knowledge vanished as empires fell and libraries decayed, and for centuries historians had no idea that such complex technology had existed. The craftsmanship of the mechanism would not be rivaled until the European Renaissance, more than a millennium later, when geared astronomical clocks began to appear. For decades after its discovery, the mechanism's true function eluded researchers. Only with X-ray imaging, 3D reconstruction, and careful archaeological study did the details emerge, revealing a device capable of modeling the cosmos with extraordinary accuracy. Even now, questions remain. How widespread was its use, and were there other similar devices that have not survived? Its rediscovery challenges assumptions about the linearity of technological progress and reminds us that human creativity is often far more advanced than history records. The Antikythera mechanism also offers insight into the worldview of its creators. By embedding the motions of the sun, moon, and planets into a single elegant machine, they expressed an understanding of the universe as an interconnected, predictable system, one in which human life and cosmic events were intertwined. It is an early manifestation of scientific thought, a physical model of celestial mechanics, and an artifact that bridges the gap between observation, calculation, and tangible interaction. Its existence demonstrates that even 2,000 years ago, humans possessed both the curiosity and the technical skill to create a miniature universe that could be studied, measured, and understood. The mystery of the Antikythera mechanism endures not only in its complexity, but in its silent testimony to lost knowledge. It is a reminder that history often conceals marvels that surpass our expectations, and that human ingenuity has always sought to grasp the vast, intricate rhythms of the cosmos. Imagining the slow rotation of its gears, one can almost feel the passage of time itself, the connection between the observer and the observed, the quiet satisfaction of understanding a fraction of the universe. In this sense, the mechanism is more than a machine. It is a bridge between centuries, between minds separated by millennia, yet united in their fascination with the heavens. As the Antikythera mechanism lies on the ocean floor or in a museum display, it invites contemplation, reflection, and wonder. Its story is one of lost brilliance, rediscovery, and the eternal human desire to understand. By studying it, we are reminded that knowledge is both fragile and enduring, that even small objects can contain vast ideas, and that the pursuit of understanding is timeless. The mechanism, in its quiet, corroded bronze, continues to turn the gears of imagination, encouraging us to marvel at what has been created, forgotten, and found again.
The Baghdad Battery is an artifact that continues to intrigue historians, archaeologists, and scientists alike, suggesting that ancient civilizations may have understood the principles of electricity long before its formal discovery in the modern era. Discovered near Baghdad, Iraq in 1938, the object consists of a clay jar approximately 13 centimeters tall, with a copper cylinder encasing an iron rod and remnants of an acidic substance such as vinegar or lemon juice inside. The design is simple yet conceptually profound, as it appears capable of producing a small electric current through a chemical reaction, functioning in principle as a primitive galvanic cell. The existence of such a device raises questions about its purpose, the knowledge of its creators, and the technological capabilities of the Parthian or Sassanid civilizations that inhabited Mesopotamia during the first few centuries CE. The origins of the Baghdad Battery are generally dated to the Parthian period, roughly between 250 BCE and 250 CE, though some scholars suggest a later Sassanid origin around the 3rd to 5th century CE. The artifacts were found in a collection alongside clay vessels and small metallic objects, indicating that they were part of a workshop or storage area. The precise cultural context is difficult to determine, as no written records explicitly describe the device or its use. The construction, however, demonstrates a level of experimental understanding of materials and chemical interactions that is remarkable for its time, suggesting that artisans or scholars were exploring practical applications of chemical energy. Functionally, the Baghdad battery may have been used to generate a weak electric current. When an acidic liquid is introduced into the jar, the combination of copper, iron, and the electrolyte creates a potential difference, producing small amounts of electricity. While modern experiments show that the current would be low and insufficient for powering modern devices, it would have been adequate for electroplating metals, producing a decorative coating on objects, or conducting minor experiments in chemistry. The electrodes themselves, composed of iron and copper, were carefully fitted and insulated, indicating an intentional design rather than a coincidental arrangement of materials. The use of organic acids such as vinegar or citrus juice would provide the necessary ionic medium to facilitate electron flow, demonstrating a rudimentary understanding of electrochemical principles. The purpose of the Baghdad battery remains uncertain, and several hypotheses have been proposed. One suggestion is that it served as an electroplating device, allowing artisans to coat gold or silver onto other metals for jewelry, ritual objects, or decorative pieces. Archaeological findings of thin metal coatings in the region support this theory, although direct evidence linking the batteries to specific artifacts is lacking. Another hypothesis is that it had a ritual or medicinal function, perhaps used in a religious or alchemical context to create sparks or stimulate perceived energy. While these ideas remain speculative, the device provides evidence that ancient cultures were experimenting with materials and processes in ways that resemble modern scientific inquiry. The impact of the Baghdad battery, if interpreted as an electrochemical device, is profound. It suggests that ancient civilizations possessed empirical knowledge of electricity long before its formal identification by scientists such as Alessandro Volta or Michael Faraday. Even if the device was not used to produce significant power, the conceptual understanding required to combine metals, an electrolyte, and a container to generate a reaction is indicative of advanced problem-solving and experimentation. It challenges assumptions about the linear progression of technological knowledge, illustrating that ingenuity and exploration were present in early societies in ways that are only partially documented by surviving artifacts and texts. The mechanics of the battery are elegantly simple. The copper cylinder acts as the positive electrode, while the iron rod serves as the negative. When the acidic solution is introduced, ions move through the liquid, facilitating electron transfer between the metals and creating a measurable voltage. The insulating clay jar prevents direct contact with external materials, ensuring that the current flows internally. The design demonstrates an understanding of both material compatibility and chemical interaction, reflecting observation and experimentation rather than accidental assembly. The uniformity of construction in multiple examples of the Baghdad battery further supports the notion that the device was intentionally produced for a specific function. The Baghdad battery remained largely forgotten until its excavation in the 20th century. Its rediscovery prompted debates about the extent of ancient scientific knowledge and the potential applications of early electrical devices. Initial skepticism questioned whether the artifact was a true battery or merely a storage vessel for scrolls or sacred items. But experimental reconstructions demonstrated its potential to generate small electrical currents, lending credibility to the electrochemical interpretation. Modern replicas have successfully produced voltage sufficient for simple electroplating experiments, reinforcing the idea that the original inventors may have understood the principles of current generation at least empirically. Shocking and curious aspects of the Baghdad battery include their potential implications for understanding ancient technology. If the device was indeed used for electroplating, it suggests that artisans could produce metallic coatings using chemical energy rather than fire alone, expanding the scope of craftsmanship in the ancient world. Additionally, the concept of harnessing electricity as a tool, even at a small scale, implies experimentation and intentional design, a precursor to the systematic exploration of physical phenomena that characterizes modern science. The mystery of how and why these devices were used continues to inspire curiosity and experimentation among historians, chemists, and archaeologists. Despite centuries of speculation, the Baghdad battery remains enigmatic. The absence of written records or detailed instructions limit our understanding, and the exact methods employed to generate electricity or perform electroplating remain uncertain. Nevertheless, the artifact embodies a spirit of innovation and experimentation, revealing that early societies explored the properties of materials, chemical reactions, and potential energy storage in ways that anticipated later discoveries. It illustrates that human curiosity and ingenuity are not confined by era or technology, and that even small, seemingly obscure objects can represent profound technical knowledge.
Roman concrete, known to the ancients as opus caementicium, was far more than a simple building material. It represented an understanding of chemistry, material science, and structural engineering that was centuries ahead of its time. A substance that allowed the Roman Empire to construct enduring monuments, aqueducts, harbors, and architectural marvels that still stand today. Unlike modern Portland cement, which relies on precise mixtures and industrial processing, Roman concrete was a natural, adaptive material that incorporated volcanic ash, lime, and aggregate in proportions that could vary according to local resources and desired properties. This flexibility, coupled with a surprising durability, made it a fundamental technology that enabled Rome to transform the Mediterranean world. The origins of Roman concrete trace back to approximately the 3rd century BCE, when Roman builders began to refine and systematize construction techniques learned from Etruscan and Greek predecessors. The Romans recognized that volcanic ash, particularly from regions like Pozzuoli near Naples, contained chemical properties that allowed the concrete to harden even underwater. This hydraulic capability was revolutionary, enabling the construction of piers, breakwaters, and bridges in coastal and riverine environments where previous civilizations had been limited to timber or stone. The process involved mixing lime, water, and volcanic ash to create a paste into which fragments of stone or brick were incorporated. As the mixture cured, chemical reactions formed strong bonds that increased over time rather than weakening, a phenomenon now understood as the formation of calcium-aluminum silicate hydrate minerals. Roman engineers had an intuitive understanding of the material's properties and knew how to exploit them for structural stability. For example, they would adjust the ratio of volcanic ash to lime depending on whether the concrete would be exposed to water or used in dry foundations. Harbors such as those in Caesarea Maritima, constructed under Herod the Great, demonstrate this mastery. The submerged concrete has endured 2,000 years of tidal and chemical stress, largely because the volcanic components react with seawater to create crystalline structures that self-heal cracks. Modern scientists examining samples of this concrete have discovered mineral growth within the microscopic voids, a natural repair system that continues to make the material stronger over time. The uses of Roman concrete were widespread and transformative. It allowed for architectural innovations such as the widespread use of arches, vaults, and domes. The Pantheon in Rome, with its unreinforced concrete dome spanning 43 meters, remains the largest of its kind in the world, a testament to the precision and understanding embedded in the material. Aqueducts, bridges, amphitheaters, and temples across the empire were constructed with concrete, often faced with brick, marble, or travertine to enhance aesthetics. The adaptability of the material permitted ambitious urban planning, as cities could be designed with large public spaces, durable roads, and complex water management systems. Concrete facilitated both practical infrastructure and monumental architecture, bridging the functional and the symbolic in Roman society.
Despite its resilience, the knowledge of how to produce Roman concrete was gradually lost after the fall of the Western Roman Empire. Political instability, economic decline, and the collapse of skilled labor networks meant that the precise mixtures and techniques were no longer systematically practiced. Medieval builders attempted to replicate the material using local lime and stone, but these early attempts produced weaker, less durable results. For centuries, it was assumed that the longevity of Roman structures was the result of luck or exceptional stonework rather than the ingenuity of a specialized material. It was not until modern material science revealed the complex chemistry of volcanic ash and lime reactions that the true sophistication of Roman concrete was appreciated. Rediscovery and analysis of Roman concrete in the 20th and 21st centuries have shed light on its remarkable properties. Chemical analysis and X-ray diffraction studies have shown that the interaction between volcanic ash and lime forms a crystalline network that grows over time. Modern researchers have even begun experimenting with eco-friendly versions of Roman concrete, seeking to emulate its durability while reducing the carbon footprint associated with Portland cement production. These efforts highlight not only the ingenuity of Roman engineers, but also the relevance of ancient technologies to contemporary challenges, including sustainable construction and climate resilience. One of the most astonishing aspects of Roman concrete is its longevity under conditions that would rapidly degrade modern concrete. Coastal piers and breakwaters, such as those at Cosa, are still standing after 2 millennia of constant wave impact, chemical corrosion, and biological growth. The mineral compounds within the concrete react with water to form new crystals, effectively filling cracks and preventing catastrophic structural failure. This self-healing property is entirely absent in conventional concrete, which relies on external maintenance or chemical additives to achieve durability. The insight that such a naturally occurring process could have been harnessed deliberately underscores the empirical brilliance of Roman engineering. Roman concrete was not merely a building material, but a catalyst for social, political, and cultural development. Its strength and versatility allowed emperors and civic leaders to undertake grand projects, demonstrating power and stability. The vast network of roads and aqueducts, supported by concrete infrastructure, facilitated trade, communication, and military movement, effectively knitting the empire together. The material was an enabler of civilization, allowing ideas, people, and resources to flow more freely than ever before. It stands as evidence that technological innovations often underpin societal transformation, with material science shaping human history as much as philosophy, law, or politics. The study of Roman concrete continues to inspire architects, engineers, and scientists. Its durability, adaptability, and environmental efficiency provide a blueprint for rethinking modern construction. By examining ancient formulations, modern engineers are discovering ways to produce concrete that not only withstands time, but also reduces environmental impact. The lessons learned from Roman concrete challenge assumptions about progress, reminding us that sometimes the wisdom of the past surpasses contemporary understanding. In this sense, the material serves as a bridge across millennia, connecting the empirical intelligence of Roman engineers with the sustainability challenges of the 21st century. In contemplating Roman concrete, one appreciates the foresight and experimentation that went into its creation. Every aqueduct, dome, and harbor wall reflect countless hours of observation, mixing, and testing, an intimate knowledge of materials and their interactions. Its rediscovery allows us to marvel at the ingenuity of an ancient civilization, to understand the interplay between chemistry, physics, and architecture, and to consider how human creativity can persist through time, leaving tangible legacies that endure long after their makers have vanished. Damascus steel, renowned for its extraordinary strength, sharpness, and distinctive wavy patterns, represents one of the most sophisticated metallurgical achievements of the medieval world. Originating in the Near East between the 3rd and 17th centuries, it became famous for producing blades that could slice through armor, maintain a razor-sharp edge, and withstand considerable bending without breaking. The steel was not named after the city of Damascus alone, though the city became a central hub for its trade and distribution. The term Damascus came to represent the entire process, a blend of iron, steel, and carbon alloys forged through techniques that were closely guarded and transmitted as trade secrets. Its creation combined art, science, and skill, resulting in weapons that were both practical tools and objects of beauty. The production of Damascus steel began with wood steel ingots imported from India and Sri Lanka, which were highly carbonized steel bars characterized by a unique crystalline structure. These ingots were heated, forged, and folded repeatedly, a process that allowed the distribution of carbon to form microscopic bands of cementite within the iron. These bands created the characteristic patterns that appear on the blade's surface, often described as flowing water or rippling waves. The combination of hardness and flexibility was achieved by controlling the carbon content precisely, a balance that modern metallurgists continue to study, seeking to replicate without completely duplicating the original methods. The uses of Damascus steel were predominantly in weaponry, most notably swords, daggers, and knives. The steel's reputation for edge retention meant that warriors could rely on their blades in combat without frequent sharpening, a crucial advantage in prolonged battles. The toughness of the material allowed for swords that could withstand impact and resist breaking during combat maneuvers. Beyond military applications, Damascus steel was also used in ceremonial and decorative objects, prized for its aesthetic appeal as much as its practical performance. A finely made Damascus blade often became a symbol of status, craftsmanship, and technological sophistication, carried by nobles, soldiers, and explorers alike. Damascus steel is notable not only for its physical properties, but also for its production techniques, which remain partially shrouded in mystery. The exact methods used by medieval smiths have been lost over time. Historical accounts describe careful heating, hammering, and folding, but many details of the chemical and thermal manipulations were never recorded. It is believed that variations in carbon content, cooling rates, and forging cycles contributed to the final material characteristics. Some blades were said to have the ability to cut through other metals or even bend without fracturing, claims that have fueled both scholarly research and legend. The interplay between empirical skill and metallurgical knowledge reflects a sophisticated understanding of material science long before the field was formally recognized. The impact of Damascus steel extended beyond the battlefield. It influenced trade, cultural exchange, and technological dissemination across continents. The steel traveled along trade routes connecting India, the Middle East, and Europe, spreading both the material and the techniques used to forge it. European smiths attempted to replicate Damascus blades, inspiring innovations in steel production that contributed to the evolution of metallurgical practices. The aesthetic qualities of the steel, its flowing patterns and polish, also influenced decorative arts and the perception of high-quality craftsmanship, establishing standards that persisted for centuries. Despite its fame, the original method for producing true Damascus steel gradually disappeared. The decline of the wood steel trade, combined with political upheavals and the loss of artisan knowledge, led to the disappearance of the material's unique properties. By the 18th century, attempts to recreate Damascus steel in Europe and the Middle East produced visually similar patterns but lacked the combination of toughness and flexibility characteristic of the original. Modern metallurgists have analyzed surviving blades using electron microscopy and spectroscopic techniques, discovering banded structures of iron carbides and identifying the presence of trace elements such as vanadium and molybdenum, which may have contributed to the steel's remarkable resilience. These studies provide insight into the lost technology and inspire contemporary efforts to reproduce similar performance using modern methods. The metallurgy of Damascus steel demonstrates an extraordinary early understanding of material properties. By controlling carbon diffusion, forging temperature, and hammering techniques, smiths were able to produce a composite material with both hardness and elasticity. The visible surface patterns were not merely decorative, they reflected the internal microstructure, a natural record of the steel's formation. The careful observation and manipulation of these materials indicate that medieval smiths had an empirical knowledge of crystallography, phase transformations, and mechanical performance, applied in a practical and repeatable manner. It represents a convergence of empirical science and artistic craftsmanship that resonates with modern materials engineering principles. In addition to swords and daggers, Damascus steel found applications in precision tools, decorative armor components, and sometimes in ceremonial or symbolic objects. Blades were often used in duels, warfare, or as prestigious gifts, enhancing the social and political influence of their owners. The steel's reputation also created an aura of mystique, with legends describing blades that could slice through rocks or retain their sharpness indefinitely. While such claims are exaggerated, they underscore the remarkable performance of the material relative to contemporaneous alternatives. Its enduring legacy continues to influence knife makers, metallurgists, and historians who seek to understand and replicate the skills of medieval artisans. The rediscovery and modern study of Damascus steel has reshaped our understanding of ancient metallurgy. Researchers have recreated variants using controlled forge welding, heat treatment, and alloying techniques, approximating the microstructure and mechanical properties of the original. Such experiments highlight the sophisticated empirical knowledge embedded in traditional methods, emphasizing that the artisans of the past possessed deep insight into material science. The combination of historical investigation, chemical analysis, and experimental replication bridges the gap between lost technology and contemporary engineering, revealing how centuries-old techniques can inspire modern innovation. Damascus steel remains emblematic of the intersection between human skill, material science, and cultural significance. It exemplifies how technical mastery can create both functional and aesthetic value, and how the loss of such knowledge can obscure the extent of human ingenuity. By studying its origins, structure, and impact, we gain insight into the sophistication of medieval metallurgical practices, the social and military context in which the steel was used, and the ongoing fascination with materials that combine resilience, precision, and beauty.
Greek fire was a weapon of unparalleled ingenuity in the Byzantium Empire, a substance capable of burning even on water, creating terror and devastation in naval battles and securing the empire's defenses for centuries. First recorded in the 7th century CE during the reign of Emperor Constantine IV, Greek fire was primarily used by the Byzantium navy to protect Constantinople from invading forces. It was described in historical accounts as a flammable liquid ejected from bronze siphons mounted on ships, designed to adhere to enemy vessels and ignite upon contact. The composition of Greek fire was a closely guarded secret, a military formula protected by the Byzantium state, and its exact ingredients remain uncertain to this day, making it one of the most mysterious and feared inventions of the medieval world. The origins of Greek fire are somewhat obscure, though it is believed to have been developed by the Byzantines as a response to the increasing naval threats posed by Arabs and other adversaries in the Mediterranean. Historians suggest that the formula may have incorporated substances such as petroleum, naphtha, quicklime, sulfur, and resin, combined in a manner that allowed the mixture to ignite spontaneously or upon contact with water. The ability to burn on water made it a revolutionary weapon, as traditional incendiary devices were largely ineffective at sea. The technology of Greek fire reflects a sophisticated understanding of chemical properties, storage, and delivery mechanisms, indicating that Byzantium engineers possessed empirical knowledge of combustible materials far ahead of their time. The primary use of Greek fire was in naval warfare, particularly during sieges and battles where controlling the seas was crucial for strategic advantage. Ships equipped with siphons could launch streams of the flammable liquid onto enemy vessels, causing immediate fire and panic. The weapon was highly effective against wooden ships, and its psychological impact was as significant as its physical destruction.
Witnesses describe the flames as impossible to extinguish with water, creating an aura of invincibility around the Byzantine fleet. Greek fire was also used defensively along the city walls of Constantinople, sprayed onto attackers attempting to scale fortifications or breach gates, demonstrating its versatility as both an offensive and defensive tool. The mechanics of Greek fire deployment were advanced for the era. Siphons mounted on ships acted as primitive flamethrowers, using a pump system to eject the combustible liquid at high velocity. Crew members operating the siphons were trained to aim accurately and maintain pressure to sustain the flow, a task that required skill and coordination. Other methods of delivery included hand-thrown pots, incendiary arrows, and tubes capable of directing flames toward specific targets. The design of these delivery systems reflects a deep understanding of fluid dynamics, combustion, and battlefield tactics, revealing a level of engineering sophistication rarely associated with the medieval period. Greek fire's impact on Byzantium military success cannot be overstated. During the sieges of Constantinople, particularly in 717 to 718 CE against Arab forces, the deployment of Greek fire played a decisive role in repelling attackers and preserving the empire. Its effectiveness allowed the Byzantines to maintain naval dominance in the Mediterranean for centuries, delaying invasions and securing trade routes. The weapon's reputation alone contributed to deterrence, as enemies feared engaging a fleet capable of unleashing flames that could not be extinguished by conventional means. Greek fire thus became both a technological and strategic cornerstone of Byzantium military policy, intertwining innovation with statecraft. The secrecy surrounding Greek fire contributed to its mystique. The exact formula was never documented in surviving texts, and those who knew the recipe were sworn to absolute secrecy. Attempts to replicate it outside the Byzantium Empire largely failed, leaving historians and scientists to speculate on its composition based on chemical analyses of residues, historical accounts, and experimental reconstruction. Modern research suggests that petroleum-based substances combined with quicklime or other reactive compounds may have been involved, producing a reaction that could ignite on contact with water or air. Despite these studies, the precise mixture remains unknown, preserving Greek fire's status as one of history's enduring technological enigmas. Greek fire also influenced the development of military engineering and chemical warfare. Its use demonstrated the potential of incendiary devices and reactive chemicals as force multipliers on the battlefield. The weapon inspired innovations in ship design, defensive architecture, and battlefield tactics, prompting adversaries to develop countermeasures such as fire-resistant coatings, distance-based engagement strategies, and fortified naval formations. In this sense, Greek fire represents an early example of technological arms races, where the introduction of a superior weapon necessitates adaptation and innovation among competing powers. Despite its legendary effectiveness, Greek fire had limitations. Its production was labor-intensive, and storage required careful handling to prevent accidental ignition. Operators faced significant risks during deployment, as exposure to the flammable liquid could result in severe injury or death. Environmental factors such as wind direction and weather conditions also affected its efficacy, making the skill of the crew crucial for successful use. Nevertheless, the advantages of Greek fire far outweighed the challenges, contributing to its reputation as one of the most formidable military inventions of the medieval world. The rediscovery of Greek fire, or at least the understanding of its probable composition, has fascinated modern historians, chemists, and military scholars.
Experiments using reconstructed mixtures based on historical descriptions demonstrate the plausibility of a substance capable of igniting on water and adhering to wooden surfaces, though exact replication remains elusive. The study of Greek fire provides insight into the empirical knowledge of medieval engineers, their ability to manipulate chemical reactions for strategic purposes, and the integration of material science into military technology. Greek fire exemplifies the convergence of practical engineering, scientific observation, and strategic application. Its creation required knowledge of chemistry, material behavior, and fluid mechanics, coupled with a sophisticated understanding of tactical needs and battlefield conditions. This combination of technical mastery and operational execution underscores the advanced state of Byzantium military technology and the ingenuity of those who sought to defend and expand their empire using innovation and creativity. In examining Greek fire, one observes a technology that was both transformative and ephemeral. Its immediate effects were dramatic, securing victories and creating fear, yet the knowledge of its exact composition gradually vanished, leaving only written accounts and physical traces. The mystery of Greek fire highlights the fragility of specialized knowledge in the absence of systematic documentation, and the ways in which strategic secrecy can preserve an invention from misuse while simultaneously rendering it enigmatic to future generations. Its story continues to captivate, providing a window into the intersection of science, engineering, and warfare in the medieval world.
The Viking sunstone represents one of the most remarkable navigational aids of the early medieval world, a crystal used to locate the position of the sun even on cloudy days or when it was below the horizon. While much of Viking navigation relied on experience, environmental cues, and knowledge of the stars, the sunstone provided a unique optical method to determine solar direction, enabling long-distance voyages across the North Atlantic, the Baltic Sea, and Northern Europe. Archaeological evidence and historical accounts suggest that the sunstone was typically a form of transparent crystal, most often Iceland spar, a naturally occurring form of calcite known for its ability to polarize light. By observing the crystal's optical properties, sailors could identify the sun's location even in challenging conditions, facilitating more precise navigation than had previously been possible. The origins of the Viking sunstone are difficult to pinpoint precisely, but references to its use appear in texts such as the medieval Icelandic sagas, which describe voyages in which the position of the sun was determined using a sunstone during overcast weather. These accounts, combined with experimental reconstructions, suggest that the Vikings possessed a practical understanding of the interaction between polarized light and crystals. Iceland spar, when rotated, produces a double image of the sun due to birefringence, and by observing the intensity and alignment of these images, navigators could determine the sun's position. This technique, while requiring skill and careful observation, allowed mariners to maintain course over open water without direct visual contact with the sun, a critical advantage for transoceanic travel in regions prone to fog, storms, and long periods of twilight. The mechanics of the sunstone rely on the optical phenomenon of polarization. Light from the sun becomes partially polarized as it scatters through the atmosphere. When sunlight passes through a birefringent crystal such as Iceland spar, it splits into two rays that are oriented at right angles to each other. By rotating the crystal and observing the relative brightness of the two images, navigators could infer the angle of the sun above the horizon, and thereby establish cardinal directions. The precision achieved depended on both the quality of the crystal and the expertise of the observer. Modern experiments have confirmed that this method is capable of determining solar position to within a few degrees, a level of accuracy sufficient for long-distance navigation across the North Atlantic. The uses of the Viking sunstone were primarily maritime. Sailors relied on the device to traverse open seas, locate islands, and maintain intended routes when the sun was obscured by clouds, fog, or the low light of northern latitudes. Its use complemented other navigational techniques, such as observations of the stars, the behavior of birds, the direction of ocean currents, and the color of the sea. By combining empirical knowledge of the natural environment with the optical aid provided by the sunstone, Viking navigators could undertake voyages of remarkable distance and complexity, reaching locations such as Greenland, Iceland, and even North America centuries before other Europeans. The impact of the sunstone on Viking society was significant, contributing to trade, exploration, and cultural exchange. Maritime expeditions enabled by such navigational tools allowed the Vikings to establish settlements, engage in commerce, and interact with distant civilizations. The sunstone thus not only facilitated practical navigation, but also indirectly supported social, economic, and cultural development. Its use demonstrates that Viking maritime expertise was not merely intuitive, but informed by technological innovation, empirical observation, and practical experimentation. Despite its effectiveness, knowledge of the Viking sunstone gradually declined with the passage of time. As magnetic compasses and other navigational instruments became widespread in the later Middle Ages, the sunstone's importance diminished. The secretive nature of Viking navigation, combined with the oral transmission of knowledge and the lack of detailed written records, contributed to the loss of practical understanding of the sunstone's use. Only through experimental archaeology and the study of medieval texts has modern science been able to reconstruct the principles behind the device and validate its functionality. The rediscovery and analysis of the Viking sunstone have been crucial in understanding both historical navigation and the scientific principles applied by the Vikings. Experiments using Iceland spar under controlled conditions have demonstrated that the crystal can reliably indicate solar direction even in diffuse lighting. Researchers have also explored alternative minerals such as cordierite or calcite from other regions to determine whether similar effects could have been achieved with locally available materials. These studies highlight the sophistication of Viking empirical science and suggest that the sunstone was not merely a symbolic or ritual object, but a practical technological solution to a real navigational problem. The practical application of the sunstone required skill, training, and attention to environmental conditions. Navigators needed to understand how to rotate the crystal, interpret the brightness of the resulting images, and translate that information into actionable directional knowledge. Observing changes in light polarization under varying cloud cover, atmospheric conditions, and time of day required careful empirical observation and adaptation. The integration of this optical tool into broader navigational practice reflects the Vikings' ability to combine technological innovation with experience, judgment, and systematic observation of the natural world. The Viking sunstone also influenced subsequent technological developments in navigation. While magnetic compasses eventually replaced optical methods in maritime exploration, the sunstone illustrates an early understanding of light behavior, empirical observation, and problem solving that foreshadows modern scientific methodology. Its rediscovery provides insight into how pre-modern societies could manipulate natural phenomena to achieve practical ends, bridging the gap between observation, experimentation, and application. Curious aspects of the sunstone include its role in transatlantic voyages, particularly in reaching Greenland and Vinland, areas previously considered inaccessible to medieval mariners. The ability to maintain course without direct visual contact with the sun would have allowed navigators to survive in conditions of extreme northern latitude, where long periods of low light could otherwise disorient even experienced sailors. The combination of crystal properties, optical knowledge, and environmental awareness illustrates a sophisticated interplay of technology and empirical skill. Its rediscovery underscores the ingenuity required to solve practical problems in environments that are challenging, unpredictable, and often hostile. In contemplating the Viking sunstone, one appreciates the blend of natural observation, optical science, and applied technology. It represents an early form of scientific thinking, in which experimentation, careful measurement, and practical application converge. The survival of this knowledge, albeit fragmented and reconstructed through modern research, reveals how human curiosity and ingenuity have long driven the exploration of the world. By studying the sunstone, modern scholars gain not only technical insight, but also a deeper understanding of the cognitive and cultural achievements of the Vikings, who traversed vast distances guided by empirical knowledge, skill, and the hidden science of light.
The Aeola pile, also known as Hero's steam engine, represents one of the earliest known devices to convert steam into rotational motion, demonstrating principles that would later underpin the development of modern mechanical engineering. Invented by Hero of Alexandria in the 1st century CE, the Aeola pile was described in his treatises on pneumatics and mechanical devices. The device consisted of a spherical or cylindrical vessel mounted on a pair of supports, containing water that could be heated to produce steam. Outward-facing nozzles or bent tubes allowed the steam to escape, creating a reactive force that caused the sphere to rotate. The mechanism is simple, yet demonstrates an understanding of pressure, fluid dynamics, and rotational motion, indicating that Hero possessed both theoretical knowledge and practical skill in engineering. The origins of the Aeola pile are closely linked to the broader intellectual environment of Hellenistic Alexandria, a city renowned for its libraries, workshops, and centers of learning. Hero's work reflects a tradition of experimental inquiry and mechanical invention, where scholars explored the properties of air, water, fire, and pressure. The Aeola pile is documented in Hero's text, Pneumatica, which includes instructions for constructing and operating the device. Hero described the method of heating water within a sealed container, allowing steam to build up pressure and escape through nozzles, arranged to create rotational movement. Although the device was primarily considered a novelty or demonstration, rather than a practical engine, it illustrates the principles of energy conversion, reaction forces, and mechanical motion, centuries before the Industrial Revolution. The mechanics of the Aeola pile involve the conversion of thermal energy into kinetic energy. When water within the vessel is heated, it vaporizes, producing steam that exerts pressure against the internal walls of the sphere. The steam exits through the angled nozzles, generating a reactive force that propels the sphere in the opposite direction. This action demonstrates the basic principle of jet propulsion, in which expelled fluid produces movement according to Newton's third law of motion. The design also incorporates a pivot or bearing system, allowing the sphere to rotate freely while maintaining balance. Hero's precise instructions indicate careful observation of the interplay between heat, pressure, and motion, and a practical understanding of how to harness natural forces for mechanical effect. The uses of the Aeola pile were largely educational and demonstrative, intended to illustrate the principles of steam and rotational motion. It may have served as a teaching tool for students or as a curiosity in temple or workshop settings, demonstrating the power of steam and the potential for motion derived from natural forces. Some scholars speculate that the device may have inspired subsequent mechanical innovations, such as water-driven automata, mechanical toys, or religious devices that moved figures or objects. Although it was not adapted into industrial use in antiquity, the Aeola pile represents a conceptual breakthrough, anticipating the basic principles of steam engines that would not be applied practically for centuries. The impact of Hero's invention lies in its conceptual significance rather than its practical application. The Aeola pile demonstrates that ancient engineers had the capacity to observe, understand, and manipulate natural forces, even if large-scale industrial use was not yet feasible. The device illustrates an early understanding of energy transformation, demonstrating that thermal energy could be harnessed to produce mechanical motion.
This conceptual leap is critical in the history of technology, showing that experimentation and theoretical understanding existed long before the steam engine became central to industrial development. Hero's work reflects a combination of scientific curiosity, craftsmanship, and a desire to explore the limits of mechanical possibility. The principles demonstrated by the Aeola pile include fluid dynamics, pressure accumulation, and reactive propulsion. By controlling the temperature of the water and the orientation of the nozzles, an operator could influence the speed and direction of rotation. The reactive motion produced by steam escaping at an angle illustrates the relationship between force, mass, and acceleration, effectively demonstrating a precursor to modern engineering principles. Observers of the device would witness a tangible manifestation of abstract physical laws, reinforcing empirical knowledge through direct experimentation. The Aeola pile exemplifies how observation, experimentation, and hands-on engagement can yield insight into natural phenomena, a method that underpins modern scientific methodology. The rediscovery and study of the Aeola pile in the modern era provide insight into the technological sophistication of Hellenistic engineering. Scholars and engineers have constructed working replicas to demonstrate the device's operation, confirming its ability to rotate and generate motion. These experiments illustrate that Hero's descriptions were precise, accurate, and grounded in practical observation. Although the Aeola pile was not utilized for industrial power in antiquity, its design anticipates the development of steam engines in the 17th and 18th centuries. Modern experiments emphasize the device's educational value, showing how even simple materials, careful design, and empirical observation can produce mechanical effects that reveal fundamental physical principles. Curious aspects of the Aeola pile included symbolic and cultural significance. In addition to demonstrating physical principles, it may have functioned as a marvel or spectacle, inspiring wonder and fascination in those who observed it. The combination of fire, steam, and motion would have appeared almost magical, reinforcing the link between scientific knowledge and observable effects. Hero's other inventions, such as automated doors, pneumatic devices, and mechanical toys, indicate a broader context in which mechanical innovation was both a practical and performative pursuit, blending education, engineering, and entertainment. The Aeola pile occupies a central place in this tradition, exemplifying both technical mastery and creative exploration. Despite its apparent simplicity, the Aeola pile requires careful construction and understanding to function correctly. The vessel must be sealed adequately to contain the steam, the nozzles precisely positioned to create rotational motion, and the heating source controlled to prevent excessive pressure or failure of the structure. These requirements demonstrate an empirical understanding of material properties, heat transfer, and structural integrity. Hero's ability to describe, construct, and operate such a device underscores the combination of observation, experimentation, and documentation that characterizes Hellenistic engineering. The device exemplifies how empirical knowledge can translate into tangible mechanical effects, laying the groundwork for future technological developments. The Aeola pile's legacy is both conceptual and inspirational. It illustrates the potential of human ingenuity to harness natural forces, demonstrates the principles of energy conversion, and provides a historical link to later innovations in steam power. By studying the device, modern engineers, historians, and educators gain insight into the origins of mechanical experimentation, the practical application of physical laws, and the ways in which curiosity and observation drive technological advancement. The Aeola pile represents an early understanding of cause and effect in mechanical systems, bridging ancient knowledge with modern scientific inquiry. In reflecting on Hero's steam engine, one observes the convergence of science, engineering, and creativity. The Aeola pile embodies principles that would later underpin entire industries, yet it existed as an intellectual and experimental tool rather than a practical source of labor. Its operation reveals the empirical knowledge of Hellenistic engineers, their attention to detail, and their capacity to manipulate energy, motion, and materials for demonstrable effects. The Aeolipile remains a symbol of human curiosity and the persistent quest to understand and apply natural forces, demonstrating that even in antiquity, the principles of mechanical engineering were accessible to those who observed, experimented, and innovated.
The Antikythera mechanism is one of the most extraordinary technological artifacts of the ancient world, often described as the first analog computer. Discovered in 1901 in a shipwreck off the coast of the Greek island of Antikythera, the device dates back to approximately 100 BCE. It consists of a complex system of interlocking bronze gears housed in a wooden frame, originally operated by turning a hand crank. The mechanism was designed to predict the movements of celestial bodies, including the sun, moon, and planets, as well as eclipses, lunar phases, and other astronomical events. Its sophistication far surpasses what had previously been thought possible for Hellenistic engineering, revealing that ancient scientists and craftsmen achieved a level of mechanical precision comparable to technology not seen again for over 1,000 years. The origin of the Antikythera mechanism is tied to the Hellenistic period, a time of intense scientific and mathematical exploration. Scholars in Alexandria and other centers of learning developed advanced theories of astronomy, mathematics, and mechanics. The device embodies this intellectual tradition, combining empirical observation with mechanical ingenuity. The complexity of its gear trains indicates knowledge of ratios, periodic cycles, and predictive modeling, demonstrating that the makers possessed a systematic understanding of the heavens. Its creation required collaboration between mathematicians, astronomers, and skilled metalworkers, illustrating a convergence of theoretical knowledge and practical craftsmanship. The mechanics of the Antikythera mechanism are both intricate and precise. The device features at least 30 gears of varying sizes, many with carefully cut teeth, arranged in multiple layers to model celestial motion accurately. A hand crank rotated the main drive, which then transmitted motion through the gear trains to display the positions of the sun, moon, and the 5 planets visible to the naked eye. Some gears accounted for the elliptical orbit of the moon, incorporating what is known as the lunar anomaly, enabling predictions of the moon's speed at different points in its orbit. Additional pointers on the dials indicated eclipse cycles and the timing of the Olympic Games, which were organized on a 4-year cycle. The combination of gears, dials, and inscriptions reveals a level of mechanical and mathematical sophistication unparalleled in antiquity. The uses of the Antikythera mechanism were primarily astronomical and calendrical. Scholars and possibly navigators could use the device to predict celestial events, organize agricultural activities, and schedule religious or civic festivals. Its ability to forecast eclipses would have had both practical and symbolic importance, as eclipses were interpreted with significant cultural and religious weight. The device may also have served as a teaching tool, illustrating complex astronomical cycles to students or members of learned circles. By encoding mathematical and observational knowledge into a tangible, manipulable object, the Antikythera mechanism allowed users to interact with abstract celestial patterns in a practical and predictive manner. The impact of the Antikythera mechanism is extraordinary in both technological and historical terms. Its construction demonstrates that ancient engineers and scientists were capable of designing, fabricating, and assembling devices of extreme mechanical complexity. The precision required to cut gears, align axles, and ensure proper transmission of motion indicates highly developed metalworking skills and a sophistication of mechanical principles. The device's rediscovery challenged previous assumptions about the technological capabilities of the ancient Greeks and the trajectory of scientific knowledge, showing that advanced engineering existed far earlier than previously believed. The principles underlying the Antikythera mechanism include gear ratios, cyclical motion, and predictive modeling. By calculating the relative rotations of different gears, the device could simulate the irregular movements of celestial bodies, according to observational data. These mechanical computations embody abstract mathematical knowledge in a tangible form, bridging theoretical astronomy with applied engineering.
The inscriptions and labels engraved on the mechanism provide additional guidance, describing cycles, dates, and instructions for interpretation. This combination of mechanical precision and written explanation reflects a comprehensive approach to knowledge, integrating multiple forms of information to achieve accurate prediction. The origin of the Antikythera mechanism is tied to the Hellenistic period, a time of intense scientific and mathematical exploration. Scholars in Alexandria and other centers of learning developed advanced theories of astronomy, mathematics, and mechanics. The device embodies this intellectual tradition, combining empirical observation with mechanical ingenuity. The complexity of its gear trains indicates knowledge of ratios, periodic cycles, and predictive modeling, demonstrating that the makers possessed a systematic understanding of the heavens. Its creation required collaboration between mathematicians, astronomers, and skilled metalworkers, illustrating a convergence of theoretical knowledge and practical craftsmanship. The mechanics of the Antikythera mechanism are both intricate and precise. The device features at least 30 gears of varying sizes, many with carefully cut teeth, arranged in multiple layers to model celestial motion accurately. A hand crank rotated the main drive, which then transmitted motion through the gear trains to display the positions of the sun, moon, and the 5 planets visible to the naked eye. Some gears accounted for the elliptical orbit of the moon, incorporating what is known as the lunar anomaly, enabling predictions of the moon's speed at different points in its orbit. Additional pointers on the dials indicated eclipse cycles and the timing of the Olympic Games, which were organized on a 4-year cycle. The combination of gears, dials, and inscriptions reveals a level of mechanical and mathematical sophistication unparalleled in antiquity. The uses of the Antikythera mechanism were primarily astronomical and calendrical. Scholars and possibly navigators could use the device to predict celestial events, organize agricultural activities, and schedule religious or civic festivals. Its ability to forecast eclipses would have had both practical and symbolic importance, as eclipses were interpreted with significant cultural and religious weight. The device may also have served as a teaching tool, illustrating complex astronomical cycles to students or members of learned circles. By encoding mathematical and observational knowledge into a tangible, manipulable object, the Antikythera mechanism allowed users to interact with abstract celestial patterns in a practical and predictive manner. The origin of the Antikythera mechanism is extraordinary in both technological and historical terms. Its construction demonstrates that ancient engineers and scientists were capable of designing, fabricating, and assembling devices of extreme mechanical complexity. The precision required to cut gears, align axles, and ensure proper transmission of motion indicates highly developed metalworking skills and a sophistication of mechanical principles. The device's rediscovery challenged previous assumptions about the technological capabilities of the ancient Greeks and the trajectory of scientific knowledge, showing that advanced engineering existed far earlier than previously believed. The principles underlying the Antikythera mechanism include gear ratios, cyclical motion, and predictive modeling. By calculating the relative rotations of different gears, the device could simulate the irregular movements of celestial bodies, according to observational data. These mechanical computations embody abstract mathematical knowledge in a tangible form, bridging theoretical astronomy with applied engineering. The inscriptions and labels engraved on the mechanism provide additional guidance, describing cycles, dates, and instructions for interpretation. This combination of mechanical precision and written explanation reflects a comprehensive approach to knowledge, integrating multiple forms of information to achieve accurate prediction. The rediscovery of the Antikythera mechanism has been a catalyst for modern research into ancient technology. X-ray imaging and 3D reconstruction techniques have revealed hidden gears and internal structures, allowing scientists to map the device's complete functionality. Analyses indicate that its design incorporated epicyclic gearing, a concept not widely used in mechanical devices until the development of astronomical clocks in the 14th century. Experimental reconstructions have confirmed that the mechanism can accurately model lunar and solar cycles, predicting eclipses within a margin of error of a day or two over decades. These findings highlight the ingenuity of its creators and the depth of their observational and mathematical expertise. Curious aspects of the Antikythera mechanism include its use of lunar cycles and eclipse prediction. The device tracks the Metinic cycle, a 19-year period after which lunar phases repeat on the same dates of the solar calendar. It also incorporates the Saros cycle, a period of approximately 18 years used to predict eclipses. These cycles were critical for scheduling religious festivals, agricultural activities, and navigation. The ability to encode such astronomical cycles mechanically required not only precise observation, but also an understanding of mathematical relationships and the application of those relationships in three-dimensional gear trains. The Antikythera mechanism thus embodies the fusion of scientific theory, observation, and practical engineering. Despite its sophistication, the Antikythera mechanism was lost to history for centuries. The knowledge of such devices disappeared, likely due to the decline of Hellenistic scientific traditions, the loss of
Automatic temple doors were remarkable engineering achievements of the Hellenistic period, designed to open and close without human intervention. These devices operated using mechanisms that combined pneumatics, weights, water, and fire in a precise arrangement. The concept was most famously developed by Heron of Alexandria, a mathematician and engineer whose works demonstrate a deep understanding of mechanics and applied physics. By creating a system that responded to heat or pressure, Heron enabled temples to appear as though they moved under divine influence, impressing worshippers and adding a mystical aura to sacred spaces. The invention exemplifies the intersection of science, religious ritual, and theatrical presentation, showing that early engineers were capable of designing devices with both practical and symbolic functions. The operation of automatic temple doors relied on principles of air expansion, water displacement, and mechanical advantage. One common design involved an altar positioned outside the temple with a concealed chamber beneath. When a fire was lit on the altar, the heat caused the air inside the chamber to expand. This expansion forced water through a siphon system into a suspended container that acted as a counterweight. As the water filled the container, its increasing weight pulled on a system of ropes, pulleys, and gears connected to the temple doors. The doors slowly and smoothly opened, giving the impression of supernatural movement. When the fire was extinguished, the air cooled, the water returned to its original chamber, and the doors closed, completing the cycle automatically. The elegance of the system lies in its simplicity and reliability, relying on natural physical phenomenon rather than complex machinery or human intervention. Automatic temple doors had profound uses beyond mere spectacle. In religious ceremonies, they reinforced the perceived presence of the divine, making rituals more immersive and memorable. Worshippers could witness a door opening seemingly on its own, enhancing the sanctity of the temple and the authority of the priests. Beyond religious contexts, similar principles were applied in theaters and public spaces, where Heron's designs could animate stages or move props without visible operators. These applications show that the invention was both a practical tool and an instrument of influence, demonstrating early human understanding of automation and audience perception. The doors also highlight a sophisticated awareness of materials, pressure control, and timing, revealing that Hellenistic engineers approached problems with both creativity and precision. The impact of automatic temple doors extended to the broader history of mechanics. By combining pneumatics, hydraulics, and counterweight systems, these devices influenced later engineers in the medieval and Renaissance periods. Knowledge of air pressure, fluid displacement, and rotational mechanics demonstrated in these doors foreshadowed developments in clocks, water engines, and other automated machinery. Automatic doors also illustrate how observation of natural forces could be applied practically, creating mechanical solutions that integrated scientific understanding with human experience. The systems relied on careful calibration. Too much water or insufficient heat would compromise the movement, requiring engineers to refine their designs meticulously. The reason automatic temple doors were forgotten largely lies in the loss of Hellenistic technical knowledge. While Heron documented many designs in his writings, the decline of the Roman and Byzantine empires, coupled with the destruction of libraries and workshops, meant that many practical applications were never widely preserved. Later civilizations rediscovered automation through trial and error, often without awareness of Heron's original devices. Archaeological studies of ancient temples and mechanical treatises reveal remnants of such mechanisms, but full reconstructions are rare. Despite this, the principles behind the doors, pressure-driven motion, counterweights, and pulley systems remained embedded in later inventions, demonstrating continuity of mechanical understanding even when direct knowledge was lost. A particularly curious aspect of automatic temple doors is the combination of physics and ritual psychology. The design ensured that the doors moved slowly and gracefully, maximizing the effect of mystery and awe. The use of fire as a trigger connected the natural element to mechanical motion, creating a tangible link between observable phenomenon and spiritual interpretation. Worshippers witnessing the doors could not easily discern the cause, experiencing the effect as miraculous. This interplay between natural law and perception reflects the early human desire to harness science in service of cultural and religious meaning, illustrating how technology and society are intertwined. Modern experiments in reconstructing Heron's automatic doors demonstrate the sophistication of his designs. By following descriptions in surviving manuscripts, engineers have recreated functional systems that replicate the opening and closing sequences. Observers note the precision and smoothness of movement, confirming that Hellenistic engineers had a highly developed practical understanding of mechanical dynamics. The reconstruction also provides insight into ancient material science. Metals, wood, and ceramics were selected and combined to withstand heat, moisture, and repeated mechanical stress. Automatic temple doors exemplify early innovation in the field of automation. They represent an understanding that motion can be driven not solely by human labor, but by harnessing environmental forces such as heat and water pressure. The systems integrate multiple disciplines, geometry, mechanics, fluid dynamics, and materials engineering into a coherent functional device. Such inventions highlight the sophistication of ancient Greek science and the creativity applied to daily life, religious practice, and spectacle. By creating a device that could operate independently and reliably, Heron demonstrated principles that resonate in modern robotics and automated systems, showing that the foundations of technology were established long before the industrial age. These doors also reflect the broader societal and cultural context in which they were used. Temples were central to community life, serving as places of worship, civic gathering, and ritual performance. By integrating automatic mechanisms, priests and engineers transformed ordinary temple architecture into dynamic, interactive experiences. The combination of technology and spirituality enhanced the perceived power of the sacred and reinforced social hierarchies, illustrating the multifaceted impact of engineering on human culture. The invention is a testament to the ingenuity of Hellenistic civilization, combining scientific knowledge, aesthetic design, and social utility into a single functional device. The rediscovery of Heron's principles in later centuries demonstrates the lasting significance of automatic temple doors. While the precise techniques were lost for long periods, the ideas informed medieval automata, Renaissance stage machinery, and early industrial mechanical devices. The doors provide an early example of integrating sensors, triggers, and motion, showing that the desire to automate processes and create predictable, controlled movement is a deeply human pursuit. Studying these inventions illuminates the ingenuity of past civilizations and provides a framework for understanding the evolution of mechanical engineering, robotics, and automated systems through history. Even today, automatic temple doors capture the imagination of historians, engineers, and enthusiasts of ancient technology. They reveal the ingenuity required to solve complex problems with the materials and knowledge available, blending science, art, and social function. These doors serve as a reminder that ancient civilizations achieved remarkable feats of engineering, often for purposes that combined utility, symbolism, and spectacle. By examining the mechanisms, materials, and cultural concept of automatic temple doors, one gains insight into how early engineers observed, experimented, and applied natural principles in ways that resonate with modern technology and thought. The legacy of automatic temple doors endures as a symbol of the inventive spirit of the Hellenistic world. They demonstrate the power of observation, creativity, and practical application in creating devices that both solve problems and inspire wonder. The careful study of these inventions informs modern engineering and robotics, providing insight into how ancient humans approached challenges with limited resources but profound ingenuity. Their combination of mechanical sophistication and psychological impact ensure that automatic temple doors remain an enduring emblem of human innovation, linking the past with present understandings of automation, engineering, and the interplay between science and society. Wood steel was a remarkable metallurgical achievement of ancient India, known for its extraordinary sharpness, flexibility, and patterned surface that would later influence the legendary Damascus steel of the Middle East. Developed as early as the 3rd century BCE, wood steel was produced through a process that combined iron ore and carbon-rich materials in sealed crucibles. These crucibles allowed the metal to reach extremely high temperatures, promoting the diffusion of carbon throughout the iron and producing a high-quality alloy. The process required careful control of temperature, cooling rates, and material proportions, demonstrating a sophisticated understanding of metallurgy long before the advent of modern chemistry. The steel was then forged into blades, tools, and other instruments, prized for their resilience, durability, and ability to maintain a sharp edge even under strenuous use. The production of wood steel began with selecting high-quality iron ores and carbon sources, such as wood chips, leaves, or charcoal. The iron and carbon were placed in a crucible, sealed with clay to prevent oxidation, and heated in a furnace to temperatures that allowed the carbon to diffuse into the molten metal. This slow, controlled process created a uniform distribution of carbon, resulting in a material with exceptional strength and toughness. Once the crucible cooled, the solid ingot could be removed and forged into desired shapes. The forging process required skill, as overheating or improper hammering could compromise the unique microstructure. Ancient Indian blacksmiths mastered these techniques, producing steel that could rival modern alloys in certain properties, a testament to empirical experimentation and deep material knowledge. Wood steel was primarily used for weapons, particularly swords and daggers, but also found applications in tools and ceremonial objects. Its superior sharpness allowed blades to cut through materials with minimal effort, while its toughness prevented breaking or chipping during combat. The patterning visible on wood steel, created by variations in carbide distribution, was not only aesthetically striking, but also an indicator of the material's quality. These patterns, sometimes forming flowing, wavy designs, became a signature of high-grade blades and contributed to their desirability across regions and cultures. Wood steel blades were traded extensively, reaching the Middle East, Persia, and even parts of Europe, influencing metallurgical traditions far beyond their place of origin. The impact of wood steel extended beyond practical utility. Its production and trade demonstrated the sophistication of ancient Indian science and industry. Blacksmiths, chemists, and artisans collaborated to refine techniques, experiment with materials, and achieve consistent quality. The export of wood steel contributed to economic networks connecting India with the Middle East and Europe, spreading knowledge of advanced metallurgy across continents. The blades crafted from wood steel were highly prized, often associated with elite warriors, royalty, and ceremonial contexts. Their resilience and beauty elevated them beyond mere tools of combat, making them symbols of skill, craftsmanship, and technological mastery. The reason wood steel was largely forgotten lies in the decline of its production techniques over time. The fall of trade networks, loss of specialized knowledge, and shifts in political and economic conditions led to the disappearance of consistent production methods. Although some blacksmiths continued forging high-quality steel in limited contexts, the precise crucible techniques, temperature control, and empirical refinements that produced true wood steel were largely lost.
Modern metallurgists have attempted to recreate wood steel using historical descriptions, archaeological evidence, and chemical analysis, but reproducing the exact microstructure remains challenging. The loss of the technique highlights the fragility of technological knowledge when transmission depends on craft expertise rather than written instruction alone. A particularly fascinating aspect of wood steel is the combination of material science and practical application. Ancient metallurgists intuitively understood the role of carbon content, temperature, and cooling in producing steel with both hardness and flexibility. The discovery that slow cooling in sealed environments produced superior properties reflects a sophisticated understanding of phase transitions and structural metallurgy, even without formal scientific theory. The microstructure, with its dispersed carbides and characteristic patterns, reveals the level of control these ancient artisans achieved through careful observation, experimentation, and iterative refinement. Their work demonstrates that practical engineering and empirical science can produce outcomes rivaling modern laboratory techniques. Wood steel also influenced the development of other metallurgical traditions. In the Middle East, it inspired Damascus steel, which became famous for its patterned blades and extraordinary cutting properties. The diffusion of knowledge occurred through trade, migration of craftsmen, and cultural exchange. The transmission of techniques illustrates how empirical technological knowledge can transcend geographic and cultural boundaries, shaping tools, weapons, and industrial practices in multiple civilizations. The influence of wood steel on later developments underscores its importance as one of the most significant metallurgical inventions of the ancient world. The mechanics of forging wood steel required not only understanding of materials, but of heat management, hammering techniques, and quenching processes. Blacksmiths needed to carefully control the temperature during repeated heating cycles to avoid fractures, maintain carbon distribution, and enhance toughness. Cooling rates were manipulated to produce the desired microstructure, with the flow of carbon-rich patterns becoming visible in the finished blade. Artisans also developed techniques for polishing and etching, revealing the beautiful banding patterns characteristic of wood steel. The interplay between science, skill, and artistry exemplifies the multidimensional nature of ancient technology, where functionality, aesthetics, and cultural value were all considered in the creation of an object. Wood steel's uses extended into ceremonial and symbolic contexts as well. High-quality blades and instruments were often presented as gifts to dignitaries, warriors, and royalty. The material itself, with its distinctive patterns and superior mechanical properties, carried symbolic significance, representing mastery of craft, intelligence, and power. Legends and historical accounts frequently highlight the almost mythical qualities of wood steel, attributing extraordinary sharpness, durability, and even magical properties to blades forged from it. These cultural narratives contributed to the lasting reputation of wood steel as a remarkable and almost mystical material, further enhancing its historical significance. Modern metallurgists studying wood steel have been fascinated by its unique combination of hardness, toughness, and aesthetic patterns. Scanning electron microscopy and metallographic analysis reveal the formation of cementite networks within a softer iron matrix, creating a material that can resist bending and chipping while maintaining a sharp edge. Experiments have confirmed that the original crucible techniques, if replicated precisely, can produce steel with properties comparable to those described in historical texts. The study of wood steel thus provides insight into ancient empirical science, revealing that systematic observation, experimentation, and iterative refinement allowed artisans to achieve results that remain impressive even by modern standards. The rediscovery of wood steel's principles continues to inspire modern metallurgists, historians, and engineers. Its production demonstrates that ancient societies were capable of producing materials with advanced mechanical properties, combining chemistry, thermodynamics, and craftsmanship in ways that prefigure modern material science. The study of wood steel highlights the continuity of human ingenuity, showing how knowledge, observation, and experimentation can create technologies that withstand the test of time. Wood steel, despite being largely forgotten for centuries, remains a testament to human ingenuity and the capacity for innovation in ancient civilizations. Its combination of functional excellence, aesthetic appeal, and symbolic significance demonstrates that technology can simultaneously serve practical needs and cultural expression. By studying wood steel, one gains insight into the advanced understanding of material science possessed by ancient Indian metallurgists, as well as the broader social, economic, and cultural networks that facilitated its production, distribution, and influence across continents. The invention exemplifies the ways in which empirical knowledge, skillful application, and cultural appreciation intersect to create technologies of enduring significance.
The Archimedes screw is one of the most enduring inventions of ancient engineering, attributed to the Greek mathematician and inventor Archimedes of Syracuse in the 3rd century BCE. It was originally designed as a simple yet effective device to move water from lower elevations to higher ones, facilitating irrigation, drainage, and water management in agricultural, urban, and industrial contexts. The device consists of a helical surface, or screw, wound around a central cylindrical shaft enclosed within a hollow tube. When the screw is rotated, water trapped in the pockets formed by the helical surface is lifted upward as the screw turns. This seemingly simple mechanism demonstrates a profound understanding of rotational mechanics, fluid dynamics, and practical problem-solving in the ancient world. The invention of the Archimedes screw reflects the ingenuity of ancient Greek engineering, combining observation of natural phenomena with creative application. Archimedes likely observed the movement of water in rivers and channels, recognizing that a rotating helical surface could transport liquid efficiently. Early versions of the screw may have been manually rotated using hand cranks, with laborers or animals providing the necessary torque. The geometry of the screw, including the pitch, diameter, and angle of inclination, determines its efficiency, allowing engineers to optimize the device for the volume of water, the height to which it is lifted, and the required speed of operation. This demonstrates a sophisticated empirical understanding of design principles even in the absence of formalized scientific theory. Archimedes screws were applied in a variety of contexts, most prominently in irrigation systems to raise water from rivers, wells, or canals to agricultural fields. By enabling efficient water transport, the device expanded the productive capacity of farmland, supporting the growth of cities and settlements in regions with variable water availability. In addition to agriculture, screws were used in draining wetlands or reclaiming marshlands, providing stable ground for habitation and cultivation. In some instances, they were employed in the movement of liquids within industrial processes, such as mining operations, where water needed to be lifted from shafts and tunnels. The versatility of the device ensured its adoption across multiple sectors, emphasizing its practical significance in the ancient world. The Archimedes screw operates on principles of helical motion and mechanical advantage. As the screw rotates, the pockets of water caught between the threads are lifted gradually along the spiral. The rotation can be powered manually with a crank or lever, or mechanically using wind, animals, or later water wheels. The continuous movement ensures that water is transferred efficiently with minimal spillage. The design demonstrates an early understanding of fluid mechanics, pressure, and the conversion of rotational energy into vertical motion. The simplicity and durability of the system made it suitable for long-term use, often requiring only occasional maintenance such as lubrication, cleaning, or replacement of worn components. In addition to its practical applications, the Archimedes screw is significant as a symbol of the fusion of theoretical and applied knowledge. Archimedes, known for his mathematical discoveries, applied his understanding of geometry and physics to create a tool that addressed real-world problems. The screw's design reflects a deep awareness of how forces, motion, and material properties interact in practical engineering. Ancient engineers needed to consider factors such as friction, material strength, and torque to ensure reliable operation. The careful selection of wood, metal, or other materials for the screw and its casing demonstrates attention to durability and performance, further illustrating the sophistication of the invention. The influence of the Archimedes screw extended well beyond its initial Greek context.
The device spread throughout the Mediterranean, being adopted by Egyptians, Romans, and later Islamic engineers for irrigation, water supply, and drainage projects. In medieval Europe, Archimedes screws were incorporated into mills, mines, and municipal waterworks. The basic principle remains in use today, with modern screws employed in wastewater treatment plants, hydropower installations, and other industrial applications. The continuity of the design across millennia attests to its effectiveness, efficiency, and adaptability. One of the remarkable aspects of the Archimedes screw is its ability to handle large volumes of water with minimal energy input. The gradual lifting process reduces turbulence and spillage, allowing for smooth, controlled transport. By adjusting the pitch and rotation speed, operators could adapt the device to different water volumes and heights. In some cases, multiple screws were arranged in series to achieve greater lifting heights, while parallel configurations increased total water throughput. These variations demonstrate an understanding of modular design, scalability, and optimization, reflecting a highly developed practical engineering mindset. The durability and resilience of the Archimedes screw made it an essential tool in regions prone to flooding or with variable water levels. By lifting water from low-lying areas, it helped prevent stagnation, reduce disease risk, and improved agricultural productivity. The ability to reclaim marshlands or maintain irrigation networks contributed to population growth, urbanization, and economic stability. In many regions, the Archimedes screw became a standard component of civic infrastructure, reflecting its integration into social, economic, and environmental systems. Its combination of simplicity, efficiency, and adaptability ensured that it remained in continuous use for centuries, often with little modification from the original design. The principle behind the Archimedes screw also illustrates early insights into energy conversion. Human or animal rotational input is transformed into the lifting of water, a form of potential energy. The helical structure allows this conversion to occur smoothly and continuously, reducing mechanical losses. By understanding the relationship between rotational speed, thread geometry, and vertical displacement, ancient engineers could optimize performance for specific applications. This empirical knowledge demonstrates a sophisticated comprehension of how mechanical systems interact with natural forces, even without formal mathematical models. Archimedes screws were not limited to water alone. Variations of the device have been used historically for transporting grain, sand, or other granular materials. The helical design allows for controlled movement of solids in addition to liquids, illustrating the versatility of the principle. By adjusting thread depth, rotation speed, and casing diameter, engineers could tailor the device for diverse applications. This adaptability underscores the broader significance of the invention, highlighting how a single concept can be applied across multiple domains, from agriculture to industry, over centuries. The historical record shows that Archimedes screws were highly valued for their reliability and longevity. Wooden and metal screws could operate for decades with regular maintenance, and the basic design required minimal specialized skills for repair. This durability made the device economically advantageous, reducing labor requirements and ensuring consistent performance. Its continued use in later periods, particularly in medieval and early modern Europe, demonstrates the lasting impact of ancient Greek engineering. The Archimedes screw represents a rare combination of conceptual elegance, practical utility, and adaptability across cultures and contexts. Even today, Archimedes screws are employed in modern engineering projects. In hydropower plants, the screw lifts water to generate electricity in small-scale installations. While in wastewater management, it moves liquid efficiently through treatment systems. The same fundamental design principles remain intact, showing the enduring effectiveness of a 2,000-year-old invention. Modern materials, motors, and engineering refinements have enhanced performance, but the underlying concept remains unchanged. The continuity of the Archimedes screw highlights the timelessness of sound engineering, demonstrating how an ancient invention can remain relevant in contemporary technological applications. The Archimedes screw, while seemingly simple, embodies the intellectual achievements of its time. It represents the translation of abstract understanding into functional design, the ability to observe natural phenomena and create mechanisms that amplify human capability. and the integration of technology into society for practical and beneficial purposes. Its long-lasting influence across centuries and civilizations underscores its significance as one of the most important and enduring inventions in human history.
Heron of Alexandria, a mathematician, engineer, and inventor of the 1st century CE, created a remarkable series of mechanical devices known as automata. These machines were designed to operate automatically, often producing movement, sound, or interaction without direct human control, relying instead on carefully arranged mechanical principles. Automata served multiple purposes, including entertainment, religious rituals, demonstration of mechanical principles, and theatrical spectacle. The invention of these devices demonstrates a sophisticated understanding of mechanics, pneumatics, and the manipulation of forces, revealing the advanced technological capabilities of Hellenistic civilization. Heron's designs combined practical ingenuity with an appreciation for drama, creating machines that impressed audiences and explored the boundaries of what was possible with mechanical systems. Heron's automata relied on a variety of mechanisms, including water pressure, air displacement, counterweights, gears, pulleys, and levers. One of the simplest examples is a mechanical bird that could move its wings and produce song when water or air pressure activated concealed bellows. Another automata involved theatrical stage effects, where statues could move, doors could open, or fountains could spout water, creating illusions of independent motion. The devices operated through precise calibration. Small changes in pressure, timing, or weight could significantly alter performance, necessitating careful observation, experimentation, and craftsmanship. Heron's writings, preserved in works such as the Automata and Pneumatica, provide detailed descriptions of the construction, operation, and underlying principles of these machines, highlighting the combination of theoretical knowledge and applied skill. The uses of Heron's automata extended into both public and private spaces. In temples, mechanical statues or moving doors enhanced religious ceremonies, inspiring awe and reinforcing the perception of divine power. In theaters, stage mechanisms created dramatic effects, moving scenery or producing sound automatically, allowing plays to incorporate elements that would have been impossible otherwise. Some automata were purely entertaining, serving as toys or novelty devices that amazed observers with motion that appeared independently. These inventions illustrate an early understanding of the psychological impact of technology, showing that engineers recognized the ability of mechanical devices to evoke emotion, wonder, and engagement in human observers. The mechanics of Heron's automata depended on principles of pneumatics, hydraulics, and kinematics. Air pressure could be manipulated using bellows or pipes to produce motion or sound, while water flow could power lifting mechanisms or spout fountains. Gears and pulleys transmitted forces in controlled ways, converting linear or rotational movement into desired motions. Counterweights and levers provided balance and regulation, allowing for smooth and predictable operation. These combinations of mechanical principles created complex machines capable of performing sequences of actions that seemed purposeful and intelligent, even though they were entirely pre-programmed by the physical configuration of components. The impact of Heron's automata is notable in both the history of engineering and the development of automated devices. By demonstrating that machines could perform coordinated movements without continuous human input, Heron laid the groundwork for concepts later seen in clocks, wind-up mechanisms, and early robotic devices. His work influenced both immediate Hellenistic engineering and, much later, European automata in the medieval and Renaissance periods. The principles explored in these devices, force transmission, timing, and energy storage, remain foundational in modern mechanical engineering, robotics, and mechatronics. One of the most fascinating aspects of Heron's automata is their combination of functional and performative purposes. In temples, the movement of statues or doors could suggest divine interaction, while in theaters, moving props and animated figures enhance storytelling.
In other cases, automata were used to teach principles of mechanics or physics, illustrating cause and effect relationships through visible, engaging demonstrations. These devices reveal that Heron understood not only the technical aspects of engineering, but also the experiential and educational potential of machines, recognizing that motion could communicate, captivate, and inspire. The uses of Heron's automata extended into both public and private spaces. In temples, mechanical statues or moving doors enhanced religious ceremonies, inspiring awe and reinforcing the perception of divine power. In theaters, stage mechanisms created dramatic effects, moving scenery or producing sound automatically, allowing plays to incorporate elements that would have been impossible otherwise. Some automata were purely entertaining, serving as toys or novelty devices that amazed observers with motion that appeared independently. These inventions illustrate an early understanding of the psychological impact of technology, showing that engineers recognize the ability of mechanical devices to evoke emotion, wonder, and engagement in human observers. The mechanics of Heron's automata depended on principles of pneumatics, hydraulics, and kinematics. Air pressure could be manipulated using bellows or pipes to produce motion or sound, while water flow could power lifting mechanisms or spout fountains. Gears and pulleys transmitted forces in controlled ways, converting linear or rotational movement into desired motions. Counterweights and levers provided balance and regulation, allowing for smooth and predictable operation. These combinations of mechanical principles created complex machines capable of performing sequences of actions that seemed purposeful and intelligent, even though they were entirely pre-programmed by the physical configuration of components. The invention of these devices demonstrates a sophisticated understanding of mechanics, pneumatics, and the manipulation of forces, revealing the advanced technological capabilities of Hellenistic civilization. Heron's designs combined practical ingenuity with an appreciation for drama, creating machines that impressed audiences and explored the boundaries of what was possible with mechanical systems. Heron's automata relied on a variety of mechanisms, including water pressure, air displacement, counterweights, gears, pulleys, and levers. One of the simplest examples is a mechanical bird that could move its wings and produce song when water or air pressure activated concealed bellows. Another automaton involved theatrical stage effects, where statues could move, doors could open, or fountains could spout water, creating illusions of independent motion. The devices operated through precise calibration. Small changes in pressure, timing, or weight could significantly alter performance, necessitating careful observation, experimentation, and craftsmanship. Heron's writings, preserved in works such as the Automata and Pneumatica, provide detailed descriptions of the construction, operation, and underlying principles of these machines, highlighting the combination of theoretical knowledge and applied skill. The uses of Heron's automata extended into both public and private spaces. In temples, mechanical statues or moving doors enhanced religious ceremonies, inspiring awe and reinforcing the perception of divine power. In theaters, stage mechanisms created dramatic effects, moving scenery or producing sound automatically, allowing plays to incorporate elements that would have been impossible otherwise. Some automata were purely entertaining, serving as toys or novelty devices that amazed observers with motion that appeared independently. These inventions illustrate an early understanding of the psychological impact of technology, showing that engineers recognize the ability of mechanical devices to evoke emotion, wonder, and engagement in human observers. The mechanics of Heron's automata depended on principles of pneumatics, hydraulics, and kinematics. Air pressure could be manipulated using bellows or pipes to produce motion or sound, while water flow could power lifting mechanisms or spout fountains. Gears and pulleys transmitted forces in controlled ways, converting linear or rotational movement into desired motions. Counterweights and levers provided balance and regulation, allowing for smooth and predictable operation. These combinations of mechanical principles created complex machines capable of performing sequences of actions that seemed purposeful and intelligent, even though they were entirely pre-programmed by the physical configuration of components. The impact of Heron's automata is notable in both the history of engineering and the development of automated devices. By demonstrating that machines could perform coordinated movements without continuous human input, Heron laid the groundwork for concepts later seen in clocks, wind-up mechanisms, and early robotic devices. His work influenced both immediate Hellenistic engineering and, much later, European automata in the medieval and Renaissance periods. The principles explored in these devices, force transmission, timing, and energy storage, remain foundational in modern mechanical engineering, robotics, and mechatronics. One of the most fascinating aspects of Heron's automata is their combination of functional and performative purposes. In temples, the movement of statues or doors could suggest divine interaction, while in theaters, moving props and animated figures enhance storytelling. In other cases, automata were used to teach principles of mechanics, illustrating cause and effect relationships through visible, engaging demonstrations. These devices reveal that Heron understood not only the technical aspects of engineering, but also the experiential and educational potential of machines, recognizing that motion.
Baghdad, during the Islamic Golden Age, became a center of scientific innovation, where scholars, engineers, and inventors developed some of the earliest mechanical clocks. These devices were designed to measure the passage of time accurately, regulate daily activities, and support religious observances, such as the 5 daily prayers. The mechanical clocks of Baghdad relied on principles of weight-driven mechanisms, gears, and escapements, integrating the knowledge of hydraulics, astronomy, and mechanical engineering that had been accumulated over centuries. Inventors adapted Greek, Persian, and Indian technologies to create systems that combine precision with aesthetic and functional sophistication, reflecting the advanced level of technical expertise in the city during this period. The design of Baghdad's mechanical clocks often incorporated water-driven mechanisms known as clepsydras, which had been used in earlier civilizations but were enhanced with gears and escapements to improve reliability and control. In these clocks, water would flow at a steady rate into a container, gradually raising a float or moving a series of levers that activated gears. The gears translated the motion into measurable time increments, often displayed on dials, rotating markers, or moving figurines. By converting the slow, continuous movement of water into regulated mechanical motion, these clocks achieved a degree of accuracy and repeatability that was unprecedented for the time. Many Baghdad mechanical clocks were designed not only to measure time, but also to produce visual or auditory signals. Automata, bells, or figures could indicate the passing of hours, announce prayer times, or provide entertainment. For instance, some clocks had mechanisms that caused small figures to strike bells or move in sequences, allowing observers to perceive time in both visual and auditory ways. These innovations illustrate an understanding of mechanical synchronization and timing, highlighting how engineers combined empirical observation with practical application to create functional, reliable, and culturally meaningful devices. The construction of these clocks required precision engineering and careful material selection. Gears were typically made of brass, iron, or other durable metals, while containers and floats for water-driven systems had to resist leakage and maintain consistent flow rates. Escapements, which controlled the release of stored energy in gears, were finely calibrated to regulate motion and prevent the device from running too fast or too slow. The integration of multiple components, gears, pulleys, weights, water reservoirs, and escapements demonstrates a sophisticated understanding of force, torque, and energy conversion, allowing inventors to produce clocks that operated reliably over extended periods. Baghdad's mechanical clocks were often large-scale public installations, serving mosques, observatories, or government buildings. They provided an essential service, regulating prayer times, civic schedules, and astronomical observations.
The visibility of these clocks also served to display the technical prowess of the city and its scholars, reflecting a culture that valued scientific achievement and the application of knowledge to everyday life. By integrating functionality with artistry, these clocks became symbols of intellectual and civic sophistication, demonstrating the intertwined nature of technology, culture, and religion in the Islamic Golden Age. Astronomical observation played a significant role in the development of Baghdad mechanical clocks. Accurate timekeeping was essential for calculating prayer times, determining the start of lunar months, and guiding navigational and agricultural activities. Engineers and scholars incorporated knowledge of celestial motion into the design of gears and indicators, allowing clocks to reflect the movements of the sun, moon, and stars. Some clocks included rotating spheres or celestial diagrams that depicted the positions of planets or constellations, bridging practical timekeeping with cosmological observation. This integration of astronomy and mechanics underscores the comprehensive nature of scientific understanding in Baghdad, where multiple disciplines informed and enhanced one another. The impact of these mechanical clocks extended beyond religious and civic use. By providing a standardized measure of time, they enabled the coordination of social, economic, and administrative activities across the city. Labor schedules, market operations, and trade could be synchronized, increasing efficiency and reducing uncertainty. Scholars could conduct experiments, record observations, and compare results with temporal precision. In this way, mechanical clocks became tools for both governance and knowledge, enhancing the organization of daily life while supporting intellectual pursuits. The innovations of Baghdad mechanical clocks influenced subsequent developments in horology, both within the Islamic world and later in medieval Europe. Knowledge of gears, escapements, and weight-driven mechanisms spread through trade, travel, and translation of scientific texts. European clockmakers incorporated principles first refined in Baghdad, leading to the evolution of tower clocks, astronomical clocks, and eventually portable timepieces. The continuity of mechanical ingenuity across regions highlights the cumulative nature of technological progress and the enduring influence of early Islamic engineering. One of the remarkable aspects of Baghdad mechanical clocks is their combination of simplicity and complexity. While the fundamental concept, the regulated flow of energy to measure time, is straightforward, the execution required careful design, precise craftsmanship, and iterative refinement. Components had to be arranged to ensure reliability, minimize friction, and maintain consistent operation over long periods. Variations in water flow, gear alignment, or environmental conditions could affect accuracy, demanding empirical problem solving and practical ingenuity. The ability to achieve such precision centuries before the development of modern timekeeping devices illustrates the advanced level of technical expertise in Baghdad. In addition to water-driven systems, some Baghdad clocks incorporated weight-driven mechanisms. Weights provided potential energy that, when released through controlled gear trains and escapements, powered the movement of dials, figures, or indicators. By adjusting the mass of weights, gear ratios, and friction in the system, inventors could regulate timing and motion with remarkable accuracy. The use of weights, pulleys, and counterbalances demonstrates an early understanding of mechanical advantage, energy storage, and transfer, which would later become fundamental concepts in engineering and physics. The aesthetic and symbolic aspects of Baghdad mechanical clocks were also significant. Many clocks were adorned with intricate carvings, inscriptions, and decorative features, reflecting both cultural and religious motifs. The movement of figures, the sound of bells, and the visible operation of gears created a sensory experience that conveyed order, rhythm, and sophistication. These clocks were not only functional instruments, but also embodiments of intellectual achievement, artistic expression, and social identity, illustrating how technology can be both practical and meaningful. Baghdad's mechanical clocks also contributed to the preservation and dissemination of knowledge. Scholars documented designs, principles, and operational techniques in manuscripts, ensuring that innovations could be studied, replicated, and adapted. These texts influenced subsequent generations of engineers, astronomers, and artisans, providing a foundation for continued exploration of timekeeping, mechanics, and automation. The combination of written knowledge and practical application reflects a culture that valued experimentation, observation, and systematic documentation, enabling technological advancements to endure across centuries. Even today, the legacy of Baghdad mechanical clocks is evident in modern timekeeping, automation, and engineering. The principles of regulated energy flow, mechanical gearing, and synchronization form the basis of clocks, watches, and numerous mechanical devices. The ingenuity of ancient Baghdad engineers demonstrates that the pursuit of precise measurement, functional design, and aesthetic integration has been a continuous human endeavor, stretching across cultures and centuries. These early clocks remind us that timekeeping, while seemingly mundane, embodies complex scientific understanding, creativity, and cultural expression. Baghdad mechanical clocks exemplify the fusion of observation, experimentation, and application. By harnessing water, weights, and mechanical linkages, inventors created devices that regulated time, guided social and religious life, and inspired wonder. They illustrate how engineering can solve practical problems while simultaneously producing beauty, spectacle, and intellectual insight. The enduring relevance of these clocks, both in historical context and in modern engineering, attest to the foresight, skill, and creativity of their creators, highlighting the sophistication of the Islamic Golden Age and its lasting contributions to human knowledge.
The Roman hypocaust system represents one of the most sophisticated methods of heating used in the ancient world. Developed during the early centuries of the Roman Empire, the hypocaust allowed buildings, particularly baths, villas, and public spaces, to maintain a controlled temperature by circulating warm air beneath floors and through walls. The term hypocaust itself derives from the Greek words hypo, meaning under, and kaustos, meaning burnt, reflecting the fundamental principle of the system. Heat generated from burning fuel was directed beneath the living spaces to create a uniform and sustainable warmth. This technology exemplifies the Romans' ability to combine practical engineering with an understanding of materials, airflow, and thermal dynamics. The construction of a hypocaust began with the creation of a raised floor supported by small pillars called pile stacks. These pillars created a hollow space beneath the floor, known as the suspensura, which allowed hot air to circulate freely. Floors were often made of tiles or stone, which conducted heat efficiently, while walls sometimes contained vertical flues or hollow channels to carry hot air upward. The heat originated from a furnace or praefurnium located outside or adjacent to the heated space. Wood, charcoal, or other combustible materials provided a steady source of thermal energy, which was carefully regulated to maintain a comfortable interior temperature. Hypocaust systems required a precise understanding of airflow and heat transfer. The hot air generated by the furnace needed to move through the underfloor space without causing structural damage or excessive smoke accumulation. Engineers carefully calculated the spacing of pile stacks, the height of the floor above the furnace, and the thickness of tiles or stone to optimize the distribution of heat. Vertical flues incorporated in walls allowed hot air to rise, warming upper portions of the room and ensuring that heat was evenly dispersed. This system provided a remarkably efficient method of heating large spaces, far superior to simple open fires or portable braziers. Roman baths, or thermae, were among the primary beneficiaries of hypocaust technology. These public spaces required controlled temperature gradients to accommodate various activities, such as warm bathing, hot steaming, and moderate relaxation. Hypocausts enabled a stratification of temperatures, where different rooms could maintain distinct thermal conditions. The caldarium, or hot bath, received the highest temperatures, while the tepidarium and frigidarium offered progressively cooler environments. This precise control allowed bathers to experience a sequence of thermal transitions, which was believed to promote health, relaxation, and social enjoyment.
In addition to public baths, wealthy Romans incorporated hypocausts into private villas, heating living quarters, dining rooms, and reception areas. These systems allowed homes to remain warm during the winter months, demonstrating that hypocaust technology was not solely functional, but also a marker of status and luxury. The installation of a hypocaust required careful planning, architectural coordination, and skilled labor, reflecting both the technical sophistication and the economic resources available to the Roman elite. The ability to integrate heating into residential and public architecture highlights the Romans' capacity to combine engineering with lifestyle and cultural priorities. The materials used in hypocaust construction were selected for both durability and thermal performance. Tiles, bricks, and stone conducted and retain heat efficiently, while mortar and clay seals prevented smoke and hot air from escaping into living areas. Floors often incorporated layers of concrete, mosaic, or tiles, which helped to distribute warmth evenly and created a smooth, durable surface suitable for heavy foot traffic. The integration of high-quality materials, combined with careful engineering, allowed hypocaust systems to operate reliably for decades, withstanding repeated heating and cooling cycles without structural degradation. Maintenance was an essential aspect of hypocaust operation. Furnaces required constant feeding with fuel, ash had to be removed, and inspection of flues and underfloor spaces ensured that airflow remained unobstructed. Skilled workers, often employed specifically for this task, monitored temperatures and adjusted fuel supply to maintain consistent heating. The attention to maintenance demonstrates that Roman engineers understood not only the principles of thermodynamics, but also the practical realities of sustaining complex mechanical systems over time. The impact of hypocausts extended beyond mere comfort. Heated spaces were believed to have therapeutic and social benefits, promoting cleanliness, hygiene, and well-being. Public baths functioned as centers of community life, where citizens gathered to bath, exercise, and socialize. The ability to maintain warm, dry environments made these spaces more inviting and functional throughout the year, enhancing public health and fostering civic engagement. Hypocausts thus contributed to both physical comfort and social cohesion, illustrating the multifaceted value of technological innovation in Roman society. Roman engineers continued to refine hypocaust design over centuries. Innovations included improved flue arrangements, multiple furnace systems for large complexes, and integration with other building features such as vaulted ceilings and decorative mosaics. These advancements optimized heat distribution, reduced fuel consumption, and enhanced the aesthetic and functional aspects of the spaces. The combination of technical refinement, architectural integration, and cultural importance reflects the sophisticated understanding that Romans possessed regarding both engineering and human experience. The rediscovery of hypocausts in modern archaeology has revealed their widespread use throughout the Roman Empire, from Britain to North Africa and the Middle East. Excavations show evidence of large-scale public bath complexes, private villas with extensive underfloor heating, and variations in design adapted to local materials and climate. These findings illustrate the adaptability and ingenuity of Roman engineers, who modified a core concept to suit different environments and purposes. The consistency of underlying principles, combined with localized adaptations, demonstrates a remarkable balance between standardization and customization in Roman technology. Hypocausts also provide insight into the broader Roman approach to engineering. The integration of heating systems into architectural design reflects a holistic perspective where multiple systems, structural, mechanical, and aesthetic, were coordinated to produce functional and harmonious environments. Roman engineers anticipated the interactions between heat, airflow, structural integrity, and human use, producing designs that were efficient, sustainable, and aligned with social and cultural goals. This comprehensive approach to problem solving highlights the advanced level of technical expertise achieved during the Roman era. In addition to practical applications, hypocausts served as a symbol of Roman innovation and authority. Public baths with elaborate heating systems conveyed civic pride and technological superiority, reinforcing the status of cities and their leaders. Private villas equipped with hypocausts demonstrated wealth, education, and sophistication. The prominence of heated spaces in both public and private life reflects the intersection of technology, culture, and social identity, illustrating that engineering in ancient Rome was as much about perception and experience as it was about function. Modern reconstructions of hypocausts, informed by archaeological findings, demonstrate the efficiency and ingenuity of these systems. Experiments show that well-designed hypocausts could maintain consistent temperatures throughout rooms using relatively modest amounts of fuel compared to open fires. The ability to distribute heat evenly, maintain airflow, and integrate aesthetic considerations underscores the technical mastery of Roman engineers. These reconstructions provide valuable insight into the practical challenges, material selection, and operational considerations in ancient heating technology. The legacy of Roman hypocausts is evident in subsequent architectural and engineering developments. Concepts of underfloor heating, ducted airflow, and controlled thermal environments persist in modern heating systems, from radiant floor heating to HVAC technology. The principles demonstrated by hypocausts, controlled distribution of heat, integration with building design, and attention to efficiency and maintenance, remain relevant to contemporary engineers and architects.
The Incan suspension bridges were remarkable examples of engineering ingenuity, constructed to traverse the steep canyons, rivers, and gorges of the Andean mountains. These bridges formed critical links within the vast Inca road system, or Capacñan, which spanned thousands of kilometers across diverse and challenging terrain. Built primarily of natural fibers, such as ichu grass, these bridges were both functional and durable, designed to support the movement of people, llamas, and goods while adapting to the dynamic environment of the Andes. The construction and maintenance of these suspension bridges illustrate the sophisticated understanding the Inca had of tensile strength, material science, and communal engineering practices, long before the advent of modern steel or iron technologies. The most common type of Incan suspension bridge was made by braiding and twisting bundles of grass to form strong ropes. These ropes were then anchored securely on either side of a canyon or riverbank, often tied to large rocks, timber posts, or stone walls. Multiple strands were braided together to create thicker, load-bearing cables, which could be tens of meters in length. The walking surface consisted of smaller, tightly woven ropes or planks tied to the main cables, forming a flexible yet surprisingly stable pathway. This design allowed the bridges to sway with wind and weight while remaining secure enough to carry daily traffic. Construction of a suspension bridge required extensive knowledge of local materials. Ichu grass, harvested from high-altitude regions, was chosen for its resilience, flexibility, and resistance to rot. The grass was soaked, twisted, and braided in precise ways to maximize tensile strength. Builders understood that the load-bearing capacity depended not only on the number of strands, but also on the quality of the weave and the tension applied during assembly. This empirical understanding of forces, combined with communal labor and careful observation, resulted in structures that could span tens of meters and endure variable weather conditions for several months to a few years before replacement was necessary. The engineering principles of Incan suspension bridges were remarkably advanced. Builders accounted for weight distribution, dynamic loads, and environmental factors, such as wind, rain, and seasonal flooding. The bridges were not rigid. Their flexibility allowed them to absorb forces without breaking, a principle modern engineers recognize in modern suspension bridges. The anchoring system was equally sophisticated, ensuring that the primary cables transferred forces efficiently to the ground or stone supports. Bridge builders also considered the gradient and approach, creating slightly arched pathways to reduce sag and maintain stability. Maintenance of these bridges was an ongoing communal effort. Because the materials were organic, exposure to sun, rain, and foot traffic weakened ropes over time. Entire communities participated in the reconstruction and replacement of bridges on a regular schedule, often annually, demonstrating an understanding of material limits, load management, and preventive engineering. This communal approach not only ensured the continued functionality of critical infrastructure, but also strengthened social cohesion and cultural identity, reinforcing the importance of collaboration and shared responsibility in Incan society. In addition to functionality, these bridges represented aesthetic and cultural significance. The sway, height, and precariousness of the crossing created experiences that were both thrilling and symbolic. In some cases, bridges were ceremonial routes used for important processions connecting sacred sites or administrative centers. Their construction required ritual knowledge and a respect for the natural environment, blending practical engineering with spiritual and cultural dimensions. The bridges exemplified a philosophy in which technology, nature, and society were intertwined, each element supporting the other to create resilient and meaningful structures. The distribution of Incan suspension bridges reflected strategic and economic priorities. Bridges were concentrated along key segments of the road network, connecting major population centers, agricultural zones, and administrative hubs. By enabling rapid communication and movement of resources, the bridges facilitated trade, governance, and military mobilization. The ability to traverse previously impassable terrain allowed the Inca Empire to maintain control over vast areas, linking remote communities to the central authority in Cusco. The bridges were thus not merely technical achievements, but instruments of empire cohesion and societal organization. Each bridge varied in size, design, and capacity depending on the location, materials available, and intended use. Some spanned only a few meters across small streams, while others, like the famous Queshuachaca Bridge, stretched over 100 meters above deep gorges. Engineers carefully assessed environmental risks, such as river flow, wind conditions, and seasonal weather, ensuring that the design could withstand both immediate and long-term stresses. The adaptability of design demonstrates an empirical, site-specific approach to engineering, where observation, experiment, and experimentation informed each construction project. The construction process involved careful preparation and coordination. Teams of skilled workers harvested and processed grass, braided ropes, and constructed the walking surface. Anchors and supports were placed and tested to ensure stability before the bridge was open to traffic. The synchronization of labor, knowledge of material properties, and adherence to precise engineering principles enabled communities to create large, complex structures using only natural materials and simple tools. The process reflected not only technical skill, but also effective organization, planning, and communication within Incan society. The mechanical behavior of Incan suspension bridges reveals an intuitive understanding of physics. The tension in cables, the distribution of weight, and the interaction between flexible and rigid components were all accounted for in design and execution. The bridges could sway, stretch, and adjust to dynamic loads, absorbing energy without catastrophic failure. This dynamic flexibility is a principle mirrored in modern suspension bridge design, where controlled movement enhances stability and resilience. The success of these bridges underscores the sophistication of empirical engineering knowledge developed by the Inca long before the formalization of mechanical science. The bridges also served educational and cultural purposes, transmitting knowledge across generations. Young members of the community participated in construction and maintenance, learning techniques of rope making, tension control, and structural observation. This hands-on training ensured the continuity of engineering skills and reinforced cultural traditions, embedding technical knowledge within social practice. The combination of functional, cultural, and educational roles demonstrates the holistic significance of these structures in Incan society. Environmental considerations played a central role in bridge construction. The Inca understood the properties of the Andes, including erosion patterns, river dynamics, and seasonal weather variations. Sites were chosen to minimize risk, maximize stability, and ensure durability. Anchors were embedded in solid rock or reinforced with stonework, and ropes were renewed before they weakened excessively.
The sustainability of these practices reflects an awareness of ecological constraints and an ability to integrate technology with natural systems. The legacy of Incan suspension bridges continues today, particularly with the annual reconstruction of Queswachaka, a living bridge maintained using traditional methods. This ongoing practice preserves not only the engineering knowledge, but also the cultural and social rituals associated with bridge building. Modern engineers study these bridges to understand principles of tensile strength, flexibility, and communal construction, demonstrating the timeless relevance of Inca ingenuity. The bridges illustrate that technology can emerge from careful observation, practical problem solving, and collaboration, creating structures that are both functional and meaningful. Incan suspension bridges exemplify a sophisticated combination of material science, engineering, and social organization. They demonstrate that complex, durable structures can be achieved using natural materials, empirical knowledge, and collective labor. By bridging gaps across treacherous terrain, these inventions enabled trade, communication, and administration while reinforcing cultural identity and technological prowess. The ingenuity, adaptability, and resilience embodied in these bridges reflect the extraordinary skill and creativity of the Inca civilization, offering enduring lessons in engineering, collaboration, and environmental integration.